All right, well, good morning, everybody. I'd like to get started with today's webinar series. This is a webinar series that is joint between the Modeling Collaboratory for Subduction Zone Systems, which is it's an RCN as part of the SZ4D initiative, but also with CIG and CSDMS. And this webinar series actually started last week, and it's looking at the role of computational geosciences in predictive assessment of plate boundary systems and hazards. And last week's series focused on induced seismicity and fault system dynamics, and today's series, which will be the first of 3 talks this week, is going to focus on quantifying the links between surface processes and tectonics. Myself, I'm Mark Bay. I'm a professor at Boston College, and Allison Duvall from the University of Washington are going to be moderating today's webinar. And today we have 2 speakers who are going to be Nicole Gasparini and Greg Tucker. Allison will introduce them in a moment, and they're going to be speaking on cyber infrastructure for modeling surface processes across different scales. But I also want to remind you that we will also have 2 additional webinars at the same time this week, on Wednesday the 20th and Thursday the 21st by Suzanne Boutier and Katie Barnhard, which are going to be looking at other aspects of coupling surface processes and tectonics. Today's webinar will, the structure of it will be talks and then some question and answers at the end. And I'm now going to turn this over to Allison, who's going to introduce today's speakers.
All right, thanks, Mark. Hi, everyone. As Mark said, I'm Allison Duvall from the University of Washington, and it's my great pleasure to introduce today's 2 speakers. So we have with us Nicole Gasparini, who is an associate professor in the Department of Earth and Environmental Sciences at Tulane University. She explores how landscapes evolve over different spatial and temporal scales, and is a co-developer of the popular Child and Landlab widely used modeling tools. Her team uses field observations, landscape modeling, remote sensing, and other data to explore questions that intersect hydrology, tectonics, and sedimentology with geomorphology at the core. She's joined by Greg Tucker, who is a professor of geological sciences and a fellow of the Cooperative Institute for Research in Environmental Sciences, known as CERES, at the University of Colorado at Boulder. His research focuses on computational and theoretical geomorphology and geoscientific software. Since 2017, he has served as the executive director of the Community Surface Dynamics Modeling System, also known as CSDMS or systems. So as Mark mentioned, we're going to have about approximately 40 minutes of presentation from Nicole and Greg today, and then that'll be followed by approximately 10 minutes of discussion and Q&A. We invite you to post your questions or comments into the Q&A box at any time during their presentations, but we're going to address them at the end. So with that, I'm going to turn it over to Nicole and Greg.
Thanks very much, Allison. This is going to be a kind of a tag team. I'll start and then I'll pass the baton over to Nicole in a few minutes. So just a quick check, everybody is seeing a title slide. Okay, so thanks everybody for joining us for this webinar series. I thought I'd start off pointing out that we would not normally start with cyber infrastructure. In some ways, it's more appropriate to start off with an overview of the science and some science examples, but because of schedule constraints, we had to do it in this order. So you're going to hear from Susanna tomorrow with sort of a flavor and overview of the science through the lens of some of her work, and then Katie on Thursday. So I thought I would start off with just a couple of quick remarks about the surface dynamics community for those of you who may be less familiar with it. So the phrase Earth surface dynamics has come to mean the collection of disciplines that Allison mentions, all those disciplines that deal with the Earth's surface, including geomorphology, sedimentology, stratigraphy, aspects of marine geology, aspects of civil engineering, and things like that. That's what we're talking about. And one of the key goals in this community of communities has been, as in other areas of geoscience, to try to come up with an ever-improving mechanistic level understanding of the processes involved and the phenomena and dynamics that those processes produce. And these pictures here give you some sense of the scope of what I'm talking about in terms of domain. We're talking about from the mountaintops down to the deep sea and its stratigraphy. And of course, one of the things that we do in this field, as in other fields, is to try to translate that theoretical understanding into numerical models. And here you see in the upper right a little example of a numerical model, which I'll say more about in a second. But one of the points to make here is that the models that are used in this community are pretty wide-ranging. If you look at this image on the left, it shows a more or less arbitrarily selected handful of models grouped according to their time scale on the horizontal axis, so going from event level things, or sort of months, days to months, all the way to geological time. And in terms of domain, from, again, the terrestrial world down to the marine realm and everything in between. And it includes things like landslide susceptibility calculations, so geohazards theme, landform evolution, fluid dynamics, representations of turbidity currents, and marine stratigraphy, to name just a few. So there's a diversity of different kinds of models, and that's both an opportunity and a challenge. Now, this little image on the right is meant to remind me to say that a couple of things. One is that in many ways, these collection of fields are at the stage where we have enough theoretical understanding that we can produce models that reproduce some of the key phenomena and patterns and forms and deposits and things that we observe in nature. But there's also a heck of a lot that we still don't know and are trying to figure out. So as a community, we now have sort of what I would describe as kind of rudimentary models that connect source to sink. And this is just one little toy example that's written using Landlab, which Nicole's going to tell you about in a few moments. So we can do this kind of thing, but it's very much a work in progress. So in talking about software, there's a couple of points I want to make about scientific software in general, because I think it's a topic that crosses the different fields that we're bringing together with this series of webinars. So when we talk about the software that's used to implement and manage and deal with numerical models, it's interesting in that it has a dual nature. It's, on the one hand, it's infrastructure. If you think about it, software is machinery. And like any other kind of hardware machinery, it requires technical expertise, it requires quality testing, it requires maintenance, every bit as much as airplanes and seismometers and things like that, even though that software infrastructure is largely invisible, which in some ways is a challenge. But at the same time, modeling software in particular is not just infrastructure, but it's also ideas. It is an embodiment of our evolving theory. And if our fields are evolving fast, as we hope they are, that means that the software infrastructure itself has to be changing, has to be adapting, has to be growing and refining. So it's sort of an extra requirement. It's not a matter of building something and then, leaving it sit on the desk for the next 15 years. It has to be flexible enough to keep up with our ideas and help us push forward. Now, one of the consequences of that, I think, is that our community and the various agencies that support our community in funding and in other ways need to make a kind of a choice when it comes to software infrastructure. And I've tried to illustrate the nature of this choice with this sort of simple cartoon sketch. On the left, and it illustrates two different, what you can think of as end-member modes of working with software infrastructure. And on the left side is the model of you build your code as you need it and set it aside when you're done. So this, for example, would be the canonical, I have a project, I want to write a paper, and I need to write a MATLAB code or something. So I hack together a MATLAB code, and I monkey with it, and I comment stuff out, I mess with it, until it just does what I want it to do. And then I switch back to the science, and I leave it behind until and unless I might happen to need it again. And that model arguably is how much of the Earth's surface dynamics community operated 15 or 20 years ago, and still to some extent is how some of us, present company included, sometimes operate today. It has an advantage in that it's efficient. If you have a piece of software that you truly only need once, then you are spending no more than the bare minimum time and effort you need to produce the science that you need to with that software. And you're not pouring in extra time and effort. But there are some downsides. Obviously, reproducibility is a challenge in that mode. You yourself might not be able to reproduce something you wrote 2 years ago if it's a slapped together thing with no comments, right? Quality control can be another concern. There's any number of stories in the scientific landscape beyond geosciences of bugs that have led to retractions of papers. And even in the biomedical community, it becomes a literal matter of life and death. So quality can be an issue. And third, there is a kind of a hidden cost. Anytime you're doing that with software that is going to be reused and is going to be needed again, then arguably in this mode, somebody's got to reinvent that wheel. And that's a kind of a hidden cost because it never really appears in formal budgets or anything like that. And nonetheless, many of us probably have experience in seeing, ourselves or somebody we work with or a student we advise essentially reinvent the wheel because the thing they need, although it's been written, is not accessible. So then if we go to the other end of the spectrum, there's the notion of software as a community resource, as a shared infrastructure that is designed for reuse, that is designed for widespread use. It's not custom built for one problem, but it's carefully designed to serve any number of problems and any number of people. And of course, that has a cost. Somebody ultimately needs to put in the extra time to document it, to quality control it, to make sure it's clean and functional and readable and standardized to some extent. All that requires effort, and that's not often a hidden cost. That is actually somebody spending time to get it to that level. On the other hand, I'll argue there's benefits to that, because when it comes to things that do need to be reused or can be reused, this can be a much more efficient way to go because it avoids a lot of wheel reinvention. And I'm sure all of you can think of examples, real examples in our communities that fall somewhere between these extremes. So in the US anyway, some maybe 15 years ago, both the solid Earth communities and the Earth surface communities were able, with support from the National Science Foundation, to launch efforts to start to put together the pieces of something that looks like this community software model. And that leads to the Cyberinfrastructure that Nicole and I are going to describe to you today. A lot of this is centered around what Mark and Allison mentioned, the Community Surface Dynamics Modeling System, CSDMS, or SysDMS if you pronounce it with a soft C. This is an NSF-supported facility founded in 2007, in many ways the sister of CIG, whose mission is to support computational modeling by promoting community software. It does this through various kinds of community coordination and engagement, development of enabling cyber tools and middleware and protocols and that kind of thing, and some hardware, and supporting various kinds of educational opportunity. It's a community of about 2,000 members currently with a range of different interests. I'll walk through a few of these and then hand the baton over to Nicole to tell you about one tool set in particular. So first of all, on the community coordination front, it's worth mentioning that one of the things that CSDMS does is to help the community come to know one another and educate one another through a series of meetings. I mention this because there's going to be a virtual meeting this May. It'll be on the theme of changing landscapes and seascapes, modeling for discovery, decision-making, and communication. So there's both a fundamental research science theme and a more applied theme. And anybody is welcome to attend, and you can find more information on the URL below. Another form of community engagement takes the form of the small integration facility that the award supports in Boulder, Colorado, partnering with individual members of the community to assist with various projects. So for example, the integration facility has 2 senior level research software engineers, so scientists turned software engineer, who have an incredible skill set and often partner on individual projects with members of the community to provide advice and guidance that'll help them turn their software artifacts from their project into things that are a little bit more standardized and a little bit more long-lasting and accessible. So that's a little bit on the community front. One of the things that we found as well is that, cyber infrastructure is human infrastructure too. And and having a community cyber infrastructure that's shared and reusable and more than the sum of the parts requires a community that is able to learn the cyber skills that they need to take advantage of these things. And that's sort of an ongoing challenge, as many of us know, right? The tech landscape is always changing. So there's an educational component of this that includes a variety of things, from short clinics at annual meetings, Jupyter Notebook tutorials on various kinds of tools, a webinar series, online documents. There's also resources for educators, many of us are educators, to use in the classroom. So for example, Jupyter Notebook-based lab exercises that students can work through to learn about a topic. So I'll turn now to some of the cyber tools themselves. You know, one of the keys to having an interoperable community cyber ecosystem is to have a way of sharing codes. And it seems simple, but it's important. And so Systems operates what's called the Model Repository. This is a collection of currently approaching 400 models and tools that community members have made available. They range from single subroutines to big comprehensive numerical codes in a whole variety of different domains. And so this is essentially a catalog and an access point to that. All these entries have standardized metadata, there's bibliographical information. You can attach a DOI to your code, you can get links to the source code, and Systems will even track an H-index for particular models, which is not the worst use of an H-index I've ever seen. So that's sharing, but that by itself doesn't create a totally interoperable system. And one of the early visions behind CSDMS was to create a modeling environment that would bring together a variety of community-built models as modules, interoperable modules that you could plug and play. And so over time, this has always been a work in progress, but over time, some of the things that we've discovered that are helpful in realizing that vision are listed here, and they collectively go by the name of the CSDMS Workbench. I won't walk through all of these, but I'll show you a couple, and then again, I'll hand it over to Nicole to tell you about one in particular, which is called Landlab. So one of the things you need, if you want to have model codes work as modules that can be plugged in and swapped in and out, there has to be some level of standardization. So Systems works with an interface standard called the Basic Model Interface. So an interface standard in the sort of hardware world is things like you get in a car and you have a steering wheel and a gear shift, and they more or less are the same whether you're in a big truck or a little electric car. In the code world, an interface standard is a list of functions, like it's literally functions. And the BMI is functions to do things like start up a code and get it ready to run, to update it. So if it's a time evolving code, you iterate a time step, to query its state variables. So whether it's temperature or pressure or topographic elevation or sediment thickness or whatever, to change state variables, right? And this actually becomes the key to coupling and experimenting with the code in real time as it's running, and then to clean up at the end. So those are 5 of what's ultimately about 30 odd functions. Now, an advantage of the BMI is that it's language agnostic, so it can in principle be implemented in almost any programming language. And that it's fairly lightweight. It's kind of the minimum set that you need to do most of the things that most numerical models do. One limitation at the moment is that we don't yet have extensions to deal with parallel architectures, domain decomposition and that kind of thing. It's something I hope will happen in the near future. I know of a couple of nascent efforts to do so, but it doesn't currently exist. At any rate, this basic model interface starts to solve the standardization problem, but part of the problem also is languages. So the Earth Surface Dynamics community, it turns out, likes to work in a variety of different languages, principally Fortran, C, C++, Python, and MATLAB, and a smattering of others. So to try to help cross the language bridge, the strategy that CSDMS has taken is to use Python as a high-level kind of lingua franca, as a top-level coupling language. And to that end, there's a set of tools called the Babelizer that will essentially provide a Python front end on top of a BMI-enabled model that's written in Fortran or C or C++, so that you can drive that model through a Python interface, even though it's written in one of these compiled languages under the hood. And that's the key to enabling a pre-existing standalone model to be able to operate as a single component in a system. So once you've got that, the next sort of ingredient you need is some kind of a coupling framework. And because we're using Python as the high-level language, the tool of choice is, again, Python. And there is a relatively simple Python package called the Python Modeling Tool, or PyMT, which is it's the tool that allows you to import these different components or modules, execute them using a BMI written in Python, couple them with one another through, for example, writing a little for loop or a little script, having exchanges or adapting different grid types with one another, and so forth. And one of the cool things about this is that it means you can now operate directly through a Python notebook or a shell. You can drive a model in a kind of a direct real-time experimental mode. You can say, go for this amount of time, stop, let me plot, let me change something, now continue, now do this, now try again, and that sort of thing. So it enables an interesting experimental mode. I would say at this point, one of the key limitations of the Python modeling tool is the limited number of components that are fully compatible. So there's about 27 of them, I guess, now, from domains ranging from permafrost to hydrology to lithosphere flexure, but it's not nearly as comprehensive as we'd ultimately like it to be. So that's where the Python modeling tool stands. And that's really designed for legacy models, for things that already independently exist as standalone things. But one of the other ingredients that ideally you'd like to have is a way that you could build complete models from smaller, more granular component parts, so that the task of building the next model that you're interested in becomes easier. You don't simply have to start from scratch and solve all the headache cyber infrastructure problems that come up. And at this point is where I hand it over to Nicole to tell you a little bit about Landlab and some applications.
Okay, thanks, Greg. That is actually, yeah, Greg and I coordinated for days on this, and it's going to work out beautifully, I can tell already. So I'm picking up right where Greg left off to talk about another aspect of the computational workbench of CSDMS, and that's going to be Landlab. So the rest of the time I'm going to focus on Landlab. And so Landlab was developed in concert with CSDMS. There was 2 primary NSF proposals, plus Katie Barnhart got a postdoctoral NSF grant, which also supported the development of Landlab. And so work on Landlab came out of, has really been done primarily through University of Washington, University of Colorado Boulder, and CSDMS in Tulane. Certainly lots and lots of additions and contributions from many people, not just in the United States, but across the globe. But the core developers are at those 3 locations. And so Landlab is not a model, but a toolkit for making models. And honestly, this has been something that has been hard to get through to people, especially Greg and I were coming really from the landscape evolution model background. And so everyone thought for sure Landlab was a landscape evolution model. And despite this amazing gift that Benjamin Camfort made with Landlab, it is not just a landscape evolution model. So I am gonna step you through that a little bit right here. So we are gonna go from logo world to Lego world. And I apologize for a lot of silliness in the rest of this talk, but I have spent much too much time with a 7-year-old and a 5-year-old in the last year, more time than really anyone should spend with a 7-year-old and a 5-year-old. So if you have not seen the Lego movie, this is a spoiler alert. So Landlab is a toolkit for building models and not a model. And what the heck does that mean? I didn't, I wasn't even sure when I started with Landlab. So if you've seen the Lego movie, you're familiar with something called Craggle, and Craggle kills dreams. So what is Craggle? It basically, takes away all the life of what Legos really should be. And Craggle is just another name for crazy glue. Okay, so you can imagine here what we have is a model of an AT-AT on the left side, and that is built with Legos. And imagine you crazy glued that together. So you would have all those building pieces of Legos and you crazy glued them together and you'd have this amazing model of an AT-AT. But that would be all it could do. It could only be an AT-AT, right? On the right-hand side, you can just see a big pile of Legos, and they have so much potential, right? They can be an AT-AT, or they can be a dollhouse, or they can be a flower garden, a spaceship, whatever you want them to be. So Landlab is more like the pile of Legos than it is like a crazy glued AT-AT. And maybe it's more appropriately something like this. So those of you who have played with Legos in recent years, they have these 3-in-1 kits where you get a bunch of Legos, and with all of those Legos, they give you directions to build, say, 3 different dinosaurs. So Landlab is sort of like that. We have a bunch of pieces and you can put them together to build lots of different models. So it's a little bit more structured than just a big old pile of Legos. But for me, this is the most apt way of describing these differences. Okay, so a kind of unique thing about Landlab is that Greg and I, and also Erkan Istanbuloglu, who were the people who sort of wrote the original proposal, we were funded to build Landlab, not really for ourselves to answer our own science questions, although we use it to answer our own science questions. We were funded to build this toolkit for our community. And so as Greg said before, it is really different than what a lot of academic software is, because we did a lot of things that we wouldn't have necessarily done if we were just planning to use it for ourselves. And so along the way, and I think Greg would probably say this too, although in his bio, he was described also as interested in software engineering, and as am I, we were sort of scientists first, right? But there's all these things that we sort of figured out along the way, of course, hugely with help from the software engineers like Eric Hutton, who's actually part of the Landlab team, and also Mark Piper and others at CSDMS have sort of taught us these ways to build this software so that it actually can be used much more easily by others and also be sustained through time. And so Greg said, if you have a piece of code that you built for yourself and you pick it up 2 years later, you may not be able to use it again if you haven't properly documented it. And I would counter that with maybe, at least for me, especially in COVID times, if I had a piece of code and I hadn't properly documented it, 2 days later, I probably wouldn't be able to use it, okay? So Landlab is sort of designed, of course, to get past those hurdles. So it's this toolkit for building models. And it's a toolkit primarily for building models of processes that happen at the Earth's surface, okay? So primarily you'd be acting on a grid of topography and seeing how that topography changes in time. But primarily, okay, so Landlab has lots of different what we call components that are part of Landlab, and these are different processes happening. Some of those components are things like vegetation, right? And so in that case, you might not necessarily care about what a grid of elevation, you might care about how much biomass is in a grid cell and looking at changes in biomass across an area. So that is something happening at the Earth's surface, and that is something that Landlab can do. And that is not a landscape evolution model, but it does have, I think for this community, what this community may be interested in, it has a lot of processes that sort of come between that intersection between the geomorphology and the tectonic community. And so some of these things are pseudo-surface, like for example, flexure is a process that is contained within Landlab. We can predict the locations of landslides, we can map layered rock properties, and so on and so forth. There's a lot there. So what you do is you take all of these different pieces and you build them together to make a model. We have many models made already that you could pick up and use, but you could also just take those individual pieces of Landlab and make your own model. Landlab is all open source. Everything is completely available via GitHub, and it's all in Python. So it's a Python library. So for any of you who are familiar with Python and Python users, you know you can use the NumPy library, and you know sort of what that means. Landlab is exactly like that. So just as you could grab everything from the NumPy library, it's a similar thing with Landlab, as long as you have Landlab on your computer. And anyone can contribute to Landlab, but we're trying to keep this sustainable. So we want to keep up sort of the good practices that are trying to make it so that anyone can add to it and it stays sort of not broken. And so part of that is we continually test Landlab to make sure that, okay, Python has upgraded, is all of our code still working? If not, we can figure out where to make those fixes. Or if I add something to code and it breaks what Greg has already written, it's okay. We can figure that out because we're constantly testing it, all right? So this Landlab library, what's there? So there's three sort of basic parts that we could divide it up into. One is the grid. So we make a grid for you. And although that may seem kind of boring, it's actually pretty important. And so you might think, well, the grid is just a bunch of points, Nicole. Who cares? It's so much more than just a bunch of points. There's points and how they connect to each other, how much area is associated with a given point. Are the points regularly distributed, or are they irregularly distributed, right? So if you look at this slide right here in the upper left, you see a raster grid. Lots of us are very familiar with raster grids. But what if you have point well data or point observations of rock type from the field? Those are usually irregularly distributed, and you can put that kind of data into Landlab and make irregular grids. So we can distribute data and make grids depending on whatever you need. So similarly with the, not just that, we have connectivity and ways to add data. So it's not just one value on the grid. There can be many, many values on the grid, and they can interact all through something what we call fields, okay? And then processes will act on those values that are on the grid, and those processes are components. And so those are some of the things like that you see at the right. So flexure and river incision, river sediment deposition in rivers, hill slope erosion. I've already mentioned plants growing and dying and landslides and all different kinds of things. So this is all part of the Landlab library. Plus we have utilities. So for example, say you want to read in a DEM, no problem, we can do that. Say you want to output an elevation grid or a grid of rock type afterwards, no problem. We can do that with many different types of file types. So this is all part of what you get from Landlab. Okay, Landlab is also extensively documented. So that's not just comments in code. And certainly like comments in code are a great, great, great start, but they're not super fun to read, let's face it. And oftentimes most code is not really well commented anyway. So this is like documentation that you can read, directions how to install, supporting materials, which are mostly Jupyter notebooks for those of you who are supporting models, which are Jupyter notebooks. And if you're not familiar with Jupyter notebooks, they intersperse basically nicely formatted text with code. So it's sort of easy to figure out what's going on with the code. And we have tutorials that are Jupyter notebooks that are both for learning Landlab and then also for learning about processes using Landlab. So we have, they're more like these Landlab models are more designed for classroom use to illustrate concepts in hydrology, tectonic geomorphology, and geomorphology. And then we also have an issues page where you can search for answers and post questions. So you actually can ask us for help, and we actually will answer, okay? So I'm just gonna show you a couple things. So this is the Landlab documentation. And as silly as it may be that I am showing you a web page, this is something that I'm really proud of, that I essentially have no part in. A lot, primarily this documentation in this current setup, we have Katie Barnhart to thank, and then also Dan Hobley before, who really did a lot of the guts of this, but the whole entire Landlab team has contributed to it. What I feel really proud about is I just want to remind everyone, there's a bunch of academics on this, and most of us are scientists, but we've figured out how to do this lovely, and when I say we, I really do mean the royal we, documentation that is like similar to what you might see from other Python libraries. And so if you look at this, you can see there's beautiful text that you can read, you can get an overview, you can look at the repository, you can see all of the code. Something that I think is super important is this, the documentation online, and you can see all of these different things, you know, description of the grid, the model, and the components. And one of the things that I like the best is looking at this. So people often ask me, like, you know, do I have it memorized? I don't have anything memorized. This is how I use Landlab. I go here and I look at all of these different descriptions of the different components that we have. And then if I were to click on one of these, it would show me what are the inputs, what are the variables that would be changed with this component. That's how I figure things out using Landlab, because, you know, literally 5 minutes later, I've forgotten what I just did, especially this year. And then another great thing is the GitHub issues pages. If you're not familiar with GitHub issues, and actually Greg showed you a GitHub issues page earlier, he just didn't call it as such. This is a place where you can both search questions that people have asked already about Landlab and then ask your own questions. And so here's the search bar, and you can search, and if you don't find anything about what the question you have and how to solve it, you can ask a question of us. And then, of course, like I said, we're all, you know, regular scientists too, so there's plenty, I shouldn't say tons, there's lots of scientific papers written, because we have to do that as well. And so I just highlight in red these two very important papers, which is sort of on the left, the first Intro to Landlab, and on the right, our version 2 release was accompanied by this paper. So if you look at all of these authors, I didn't name authors by name. These are really the core initial developers, and then people have been added on to the team and come and go. And then of course, we have lots and lots of other people who are contributing. And so there's lots of different papers on, say, different components, how components have been used, so on and so forth. This is just an example. Okay, so enough of this. Let's see a little bit about what Landlab can actually do. So this is an example from a former PhD student of mine, Jordan Adams, and this is routing a flood wave across a landscape. So on the bottom, you see a hydrograph at the watershed outlet. And this is actually not something that landscape evolution models typically do. They do not route flood hydrographs, they route steady state flow. So there is not a change in discharge through time when you assume steady state flow. So this was something that we have in Landlab now. Here's an example of a hogback that Greg made using the cellular model. And this is probably a landscape feature that many of you have seen before and know. And then here's the lithology component that Katie Barnhart put together. And this is just a really cool visualization of how uplifting layers of soft and hard rock can impact landscape evolution. Okay, so in the last, one more example. This is an example of drainage rearrangement, and this is from Nathan Lyons. And what Nathan is showing here is if you perturb a landscape, and this is pretty dramatic perturbation. So if you have rivers flowing north and south on the left-hand side, and you dam up all those rivers, and then all of a sudden you open up and have all flow either going to east or west, how will the landscape adapt and change? And what you can see, this evolution is happening on the left-hand side, but it's kind of not much happening. It's a little bit boring, right? Now, eyes visually, you can see there's a difference here. For those of you who are not fluvial geomorphologists, this has higher drainage density. So what it just means is that the hill slopes are shorter and the rivers eat further up the hill slope in this landscape here. And what you can see is that when we perturb this landscape, it will react and rearrange itself much faster, okay? So we can do these kind of science, ask these kind of science questions using Landlab. Okay, I'm just going to quickly go over some new directions, and this is from my graduate student, Christian Kakonkwe, and what he's doing is using Landlab to explore source-to-sink sediment routing. And so what he's modeling is here is a fault system. Here you have uplift, and here you have subsidence, and you have sediment and water can leave three sides of this system. Okay, and we're going to erode it. There's going to be hill slope diffusion, and then there's going to be erosion, sediment transport, and deposition happening across this landscape. So what Christian finds is that when you have this linked source to sink system, you can evolve topography to reach a dynamic equilibrium. And so if you just look at the elevation time series at these 3 points, so here we're going from fault to distal. So from fault to distal, what you can see is after some time, the elevation levels off and you reach a dynamic equilibrium. When you look in the sink, the same thing happens, but what you see is a lot more variability. So even though the system has reached an equilibrium, there's still changes in elevation. And there are also up here small changes. They're just very, very small. But there is more dynamics than you would get if you did not couple a source to sink system, okay? So if you just model the source, you don't get the same dynamics as when you couple the source to sink system. Okay, so I just wanna show you, I'm just gonna fast forward this to the dynamic equilibrium phase. And what you can see is you look at these channel profiles here and you can see there's some little kind of flickering. That flickering is actually triggered by changes that are happening in the sink. You can't see the sink resolved in this color bar, but there's changes happening in the sink that perturb what's going on in the source, and you can actually get these sort of autogenically created nick points. So this is pretty fun stuff that Christian has been looking at. He can also look at the deposits in the sink, and he can map out things like the Sadler effect. So for those of you who are not familiar with the Sadler effect says that when you look at sediment that's deposited, if you measure that deposition rate over different time scales, you would get a different average deposition rate. And usually when you average over short time scales, you might get a much higher deposition rate than when you average over longer time scales, because you're incorporating those hiatuses. And in fact, you get that exact same thing. So here, what you see, this is furthest from the fault, and here's proximal to the fault. And proximal to the fault, you have higher deposition rates, you have a higher subsidence rate there too. And what you can see, this x-axis is the time span over which you're averaging. The longer your time span, the smaller your deposition rate. And in fact, if you average over a long enough time span, your deposition rate is going to exactly be matched by what your forcing rate or your subsidence rate is, okay? And so this is actually something that's used in the stratigraphy community to figure out timescales of where autogenics versus allogenics are dominating the system. So we have the ability to do that in Landlab now. And here's just another movie that Christian made. This is all from Christian, and this is just looking at the stratigraphy, so on the left we have, this is the fault, and then this is distal, and then this is this, I guess, parallel to the fault, a cross section of building the stratigraphy. So imagine we can go into this stratigraphy and we can start to query it and start to ask questions of what's being recorded of events that are happening in the source. And similarly, how does what goes on in the sink influence the source? And with that, I think I am done and we are ready to take questions.
Great, thank you so much to both Nicole and Greg for really exciting presentations with lots to think about. So I'm gonna check in on the Q&A box here. Again, we ask that you please, if possible, put your questions into the Q&A. I'll read these out loud and then we'll give Nicole and Greg a chance to answer them live. So we have our first question from Riza Madoff, which is, what are the parameters for the model processes based on? Collections of field data or mathematical models? That's the question. And then what are the chances of parameters getting reformulated with new studies?
Do you want to take? I can start. So the question, that is a great question. And the answer is mostly the parameters. It kind of depends. So there are some things, like the different components represent different processes. So the different parameters vary from component to component. So there might be some things that you're pretty familiar with, like, for example, Manning-Zen. Okay, so Manning-Zen is something that's in there, and you can't, I guess there are kind of ways you can measure Manning-Zen, but it's sort of something you feel out. You look at the river and you can figure it out. So there's parameters in there like that. But there's also parameters that actually there's really no way to measure from the field. And it's more sort of like fitting to relationships. So it really depends, but you asked a really important question, is like, what if we get new data, or what if our understanding of process evolves through times or changes through time? That's great. We can always build new components to look at sort of our new understanding, if we can quantify that and put it into an equation. Or we can always modify existing components to add something in to take into account something that we didn't realize, or like a measurement that we didn't know we could make from before. Greg, do you want to add anything?
That was great, Nicole. And it's a great question, Risa. I think, I would just say, I think this is where a lot of the science is happening. Some may not be familiar with this concept of geomorphic transport laws, which was introduced by Bill Dietrich and colleagues in a paper some time ago, where a geomorphic transport law is a mathematical expression of some process. An example would be the diffusion equation as a representation of how fast soil creeps down a slope on average. And a lot of the science is happening in unpacking the black boxes that go into those rules. So, there's been any number of papers published to pick up on that example in the last X number of years, trying to unpack the effective rate coefficient that goes into that. That's an example where there are methods to back out what the effective rate coefficient is, but it's still kind of a lumped coefficient that has been applied to many different processes, and people are still actively trying to unpack it.
Great, thanks. The next question is from Claudio Ficina, who says, excellent talk. One question, do you have isostasy in your system? And I'm assuming that's specific to Landlab, but you could comment on other models in the CSDMS system as well.
Isostasy, I think we do, right, Greg? I mean, isostasy would just be modeled by flexure. So yes, we do in Landlab.
And there's also a piece of code written by Andy Wickert at the University of Minnesota called GFlex that, if I remember right, I don't know if Andy's on the call to answer the question properly, but I believe he might have some viscoelastic capability in that. I'm not positive of that. but you know, that's an example of where, so, okay, so if you want to do uniform rigidity, 2D plate flexure, that's definitely there. There's a component for that. I think Andy's model does non-uniform rigidity. And if you wanted something more sophisticated than that, you'd have to write a new component or make a component in PyMT.
Great. So while more questions are getting typed into the chat, I wondered if I could just pose a question for discussion to both of you in terms of barriers to entry. I just thought it might be useful given there's over 100 people on this call, and some of them probably come from various backgrounds and various experience in the modeling world. And I wondered if you could talk a little bit about kind of, what kind of skills do you need to have? How hard is it to get involved? How can people get involved who may not have been involved before? Or, if you just want to say a few words about barriers to entry.
That's a great question, Alison. I could start taking a stab at it and see what Nicole thinks. I've thought a lot about this because, we want to be scientists and focus on our science. We're not software engineers. On the other hand, we need to know something, right? I mean, we need, people who work in geochemical labs need to know how to use their mass specs and things like that. And in fact, from my own personal experience, there's sort of a chain of things you need to get involved in some of the kinds of modeling that Nicole has showed you. And it starts with, just the fundamentals of knowing something about how to take a geophysical system of some sort and translate it into mathematics. That's a skill that has nothing to do with computing. It's something that's taught in some geoscience programs and not in others, I think. But it's a really important skill, and there are some good books that are helpful. I mean, one that I really like is written by Rudy Slingland and Lee Kump as an introduction to mathematical modeling. So there's that side of things. And then there's a set of computational skills. I mean, somebody needs to program, and most of us, and this is true across more sciences than just this geoscience. So, actually people who study software use in the sciences generally find that a large fraction of scientists are self-taught in computational work, in programming and things like that. And so, you need to know how to program, you need to know some numerical methods for many of these kinds of things, and that's often at least a semester course somewhere. And then there are some various tips and tricks that apply to, I guess, what you might call modern scientific computing, that include things like how to test your code and how to use version control and things like that. What do you think, Nicole?
Well, first off, I would say if there's any students out there, take a programming course. If you take one programming course, it will certainly open up the doors to other languages. So I really can't emphasize enough how important that is. And even if you don't see yourself as a modeler, programming is important for data management, data analysis. It just, so no matter what, those skills are gonna be fantastic. For those of you who don't have sort of the opportunity to do that anymore because you're at a different career stage, I really can't tout things like CIG and CSDMS enough. So if you were to go to CSDMS and look, there's a whole series of webinars that are posted there on things like, there is one from Greg about Landlab and getting started in Landlab. There's a whole series on leveling up and improving your coding skills and on your software development skills. Those things, I send my students there all the time to learn stuff and to sort of get an idea of, well, here's what you should be doing. I also love that Klump and Slingerland book. But I really think, a lot of this is something that there's a lot of resources out there, and it's not always necessarily easy to find. So go to existing infrastructure like CSDMS or CIG to get some support. But that being said, there's also the meetings and the clinics. We do things on Landlab trainings a lot. CSDMS nearly always has a training on Landlab, but also lots of other types of modeling. There's SPIN, which is a summer school that some of us are running out of CSDMS to learn how to get sort of entry into modeling. So there's lots of different things. If you just start Googling and looking around, and definitely start with CSDMS.
All right, great. That's awesome. Yeah, I think it's wonderful to hear about all these really comprehensive resources that are available. So I see there are a few more questions in the Q&A box. So we'll try and get to those here in our last 5 minutes. So we have a question from Ricardo Raitano, who says, thank you for the great talk. I really appreciate the community vision you are proposing. Is it possible to implement Landlab with other tools to directly analyze the model's metrics obtained using Landlab, e.g. Toppo Toolbox?
Yeah, that's an easy one. You can certainly do that. One of the design goals was to use standard file formats. So you can output data from a Landlab built code as, for example, netcdf or arc-ASCII files, the kinds of things that I think Toppo Toolbox is probably designed to read.
Great. Next question is from Ian Dubinsky, who asks, has Landlab been applied outside of pure research? For example, EIAs, engineering design studies, or regulatory issues? And would you want to see this usage for Landlab and incorporation of such applications into CSDMS community in general?
Well, I know, so for example, we pointed to, there's a landslide component, and the landslide component is predicting landslide susceptibility. And that is a project that was run from Erkan Istanbuloglu's group out of University of Washington. And Rhonda Strauch was the leader on that project. And that was designed to help land managers in the Pacific Northwest manage land and think about susceptibility and where things might fail and where they may need to have, areas that are more hazardous. So that's one example. Greg, I don't know if you want to jump in with others.
Well, just to say that I think you're going to hear on Thursday from Katie an example of one project that really was motivated originally by a really applied need, that was long-term erosion forecasting at a hazardous waste site. So the answer is yes, and I'm told that there are some consulting firms that have picked up Landlab and are using it for something. Honestly, I have no idea. A lot of the new applications are people we've never met and aren't in direct contact with, which is wonderful. That's exactly what we want to see happen with community software. But I think it's starting to get used.
Fantastic, and that's good. Good to get you all excited for Katie's presentation on Thursday. Good motivation for that. So I think this will probably be our last question for today from Osaji Ebeyiro, who says, thanks for the excellent presentation. Is there room for forward modeling in your system?
By forward modeling, I think you may mean like take a current landscape and do some stuff to it. Absolutely, you can do that. I don't know. Is there more? Am I missing something, Greg? Should you?
Yeah, if you want to follow up and type into the question again, to the question asker, if you're thinking about prediction or what specifically you're thinking about in terms of your question, you can follow up.
Yeah, I guess I would just add that when I hear the phrase forward modeling, I think of it as opposed to inverse modeling. So with forward modeling, you have a set of equations or algorithms, and you start with a particular condition and you advance forward in time, or sometimes forward in space, whatever forward means. And inverse modeling is you have a set of data maybe it's it's classically done in exploration geophysics, for example, where you are trying to fit a set of equations or algorithms to a set of data. And that often involves iterative forward modeling. So you do lots and lots of forward modeling until you find the best fit to your data. And so in that sense, forward modeling is much easier. Again, I think on Thursday, you're going to hear from Katie an example of inverse modeling.
Great. All right, well, thank you. I think we'll take this moment to say thank you again to Greg and Nicole for this fantastic webinar today. No one else can hear all the clapping, but you can imagine it. And I will say that I really hope that you can all join us again for Suzanne's presentation tomorrow and Katie's presentation on Thursday. And note also that all of these are being recorded and will soon be available on the MCS website. All right, thank you again, everyone, and I hope you have a great rest of your day.